Okay, good evening, everyone. Hello, Hao Ming. Hello, Wen. Thank you for being here on time. Okay, my name is Mr. Chu. Okay, and today we'll be doing the theory on the topic of sound for O-level physics. Okay, so for Hao Ming and Wen, can both of you please on your camera? Okay, thank you, Wen. Hao Ming, can you please on your camera? Okay, so let's begin. So today we'll be doing the last topic for wave. Okay, so I'd like to show this mind map to all of you. Okay, so we're now on the red color branch. Okay, on the red color branch, last two lessons we completed electromagnetic spectrum. Okay, and then this okay, for today and the next two lessons we'll be going through sound. Okay, so for your this will be the number of topics that you all have. Okay, if you were to see next year's syllabus, your juniors, they will be no longer learning sound. Yeah, but don't be so happy. All the sound topic are all squeezed into the wave topic. Okay, so they are still learning sound, they have lesser topic, but a lot of things are all compressed together. Okay, so yeah, next year you will no longer see the topic of sound, but the topic of sound, 95% of the content will be taught under wave property. Okay, so that will be what's happening to the syllabus, slight change, but not much. Okay, less topic, but it's all under wave. Okay, so they'll be taught sound under wave first, then EM spectrum, then light. Okay, so this is how it goes. After we do 3 weeks of sound, or 4 weeks of sound, okay, then we'll move on to the electricity and magnetism branch. Okay, so any question for me regarding sound? So can both of you, Wen and Hao Ming, share with me what topic is your school teaching you now? Okay, Hao Ming is on sound, so just nice. How about for Wen? What is your school teaching you now? Kinetic what? Kinetic, kinetic model of matter. The one on top here. Okay. So for Wen, the topic before this, what did your school teach you? Okay, same thing for Hao Ming. What is the topic that your school teach you before this topic? What is the topic taught before this? So EM spectrum or just wave. Okay, so for Wen is thermal property of metals. Okay, so for Hao Ming, have your school taught your light and EM spectrum yet? These two topics. Okay, Wen your school has finished all the red topic, right? So today will be revision. Okay, Wen the red topic. Your school has finished all the 4 red topic, right? Just wave, light, yes, no. Hey, help me make up your mind. Are you start listening in class? Okay, anyway, I roughly have an idea where your school is doing. How many is on wave? Okay, so let's continue. Okay, let me share with you what you are required to know. Okay, for sound. Okay, so I'll share with you all the syllabus first. Let me find the syllabus. Here. Okay, so no, this is the hold on. Okay, so for the topic of sound is broken up into the 4 topics. Okay, sound wave, speed of sound, echo, and ultrasound. Okay, so I'm going to share with you, okay, what is this whole topic about. Okay, before you all learn sound, okay, you all have learned about general wave property. So let me just revise a few things on general wave property. Okay, so number one, all of you need to know that this relationship, okay, V equal to F lambda. Okay, so for whether is it electromagnetic spectrum or is it sound, okay, all wave will actually obey this relationship. Okay, V equal to F lambda. Okay, so the second thing that all of you also need to know, okay, is that there are 2 types of wave. Okay, longitudinal and transverse. So for sound, in the topic of sound, okay, all the sound wave are longitudinal wave. Okay. Wenxuan, I have sent the notes to you already. Just get from your parents about 2 days ago. Your school also got notes, right? Actually, I don't know why you want so many notes. It's just that more and more paper. Okay, so I'm just going to teach you the concept lah. Okay, so sound wave are all longitudinal. Okay, sound wave are all longitudinal. Okay, what's the difference between transverse and longitudinal? Okay, so before I talk about the difference between these two, let me first talk about what is a wave. Okay, a wave transfer energy, okay, from one end to the other end without transferring matter. Okay, what does this mean? Okay, so for example, if there's nothing is moving, I got 4 particles here. 1, 2, 3, 4, or I put 5 particles. Okay, there are 5 particles here. The particle, when there's energy passing through them, they will start to vibrate. Is that clear? If they start to vibrate. Okay, so energy, let's say, is moved from left to right. So when the energy is moving from left to right, all these green dots, they do not actually move from left to right. They will vibrate about this point. They will vibrate up, down, or left, right. Is that clear? Okay, that is what wave is about. So when energy is being transferred from point 1 all the way to point 5, this 5 point will not move from left to right. It only vibrate about the point. Is that clear? Okay, so how do they vibrate? Let me explain to you all. Okay, let me draw the 5 dots. Okay, the 6 dots. Okay, so for sound wave, the energy that is being transmitted is sound energy. Is that clear? If it's light, visible light will be light energy. Okay, so if it's things like infrared or microwave, it will be thermal energy and so on. So the energy is being transmitted, let's say, from left to right. Okay, clear so far? So how does the wave actually, how does the matter react? Okay, so first of all, let's talk about longitudinal. I use green. So for longitudinal, all of these will vibrate left and right. Okay, all of these will vibrate left and right. Is that clear? Okay, all of them will vibrate left and right. Okay, so if they are vibrating left and right, okay, so at some point they will be close together. Okay? At some point they are close together. Then at other points they'll be far apart. Clear so far? So for example, this dot never moved. Okay, this dot moved to the left. This dot moved to the left. Sorry, the first dot moved to the right. So they are all clustered together. Okay, we will call them, they are being compressed. Is that clear? They are being compressed. Okay, then this one also moved to the right. This one did not move. The last one moved to the left. So these 3 together, they are being compressed. Okay, so the green color that I'm drawing, okay, is what we call longitudinal wave. Okay, where the matter, okay, the matter that I'm drawing, the dots, they are not moving from left to right, but they are just moving in the same direction as the energy. Okay, parallel to the energy. So they are all moving left and right, left and right. The direction is parallel to the energy. Is that clear? Okay, so this is what longitudinal wave is. Okay, so what is transverse wave? Okay, I'll use the blue color to explain. Transverse wave is when the thing actually vibrate up and down. Is that clear? It actually vibrate up and down. Okay, so if the first one may not move anything, you'll move up. Okay, you'll move up and then it'll come down. Okay, so the energy is being transmitted from left to right, but all these dot, okay, is moving up and down. Clear so far? Okay, so can you see down here? If it's moving up and down, it is perpendicular to the direction of the energy. Okay, so this is what you all need to know for general wave property. Okay, for the longitudinal and transverse wave. Understand so far? Okay, so for electromagnetic spectrum, just a revision, it can actually be transmitted without a medium. Okay, without a medium, meaning that it can actually move through vacuum. Okay, so electromagnetic spectrum can actually transfer energy, okay, through vacuum. Okay, but when they move across from left to right, the particles move up and down. Okay, the light particle and so on move up and down. It doesn't move from left to right. It's the energy that is being moving. Clear? Okay, whereas for sound, when they need to move from left to right, how the energy is being transferred is by the vibration of the particles, whether is it solid, liquid, or gas. Okay, so the particle will vibrate, hit the other particle, and the energy is being transferred from particle to particle. So they need to actually hit each other. Okay, so for sound wave, you need particles for transmission. Okay, basically you need to have a medium. Is that clear? Okay, so this is some of the differences between electromagnetic spectrum as well as sound wave. Okay, so all the points so far are we all clear? If you are clear, give me a thumbs up. If you are not clear, give me a thumbs down. Is there a thumbs down? Okay, thank you, Hao Mi. Wen-Shen, you okay? Okay, Wen-Shen, please on your camera. Okay, Wen-Shen, you understand so far the difference between longitudinal and transverse, and the difference between sound wave and EM wave. Okay, Wen-Shen asked a question. So does it move up and down like transverse? Okay, no. Okay, you're asking about the sound wave, is it? Sound wave, the particles, it could be air, it could be water. Okay, the particle itself move left and right. Okay, so if the energy is moving from left to right, you'll vibrate not up and down, but left and right. So you'll just vibrate the same direction as the energy. But it doesn't go with the energy, it just vibrate about the same direction as the energy. Okay, but for transverse, it actually vibrate up and down. Okay, vibrate up and down. Can? Are you okay? Okay, so I just revised a bit of the general wave formula. Okay, so let me go back to what you need to know about wave. Okay, so for wave itself, you will need to be able to describe how is sound produced. Okay, how is sound produced? Basically, you need to vibrate certain things at a certain frequency, okay, and then sound will be produced. Okay, so for example, if you touch a speaker, can you feel vibration? Okay, why is there vibration? It's because it is the vibration that produce sound. Okay, I repeat again. It's the vibration of the speaker that produce the sound. So things need to vibrate, then you'll be sound. Okay, the vibration is not left, right, left, this slow. The vibration is much faster. Okay, how fast? Maybe let me share with you. How much can our ear, can a human listen? What's the frequency that our human ear can hear? How many? That is the speed of the sound. Okay, so sound that human can hear is actually from 20 hertz to 20 kilohertz. Okay, that is for a pure human, but we human are not pure, right? As we get older, we will not be able to hear 20 kilohertz, maybe 16, maybe 15. Is that clear? Okay, how to tell how high can we hear? Okay, you all can go to YouTube, go and find those mosquito ringtone or those type of frequency sound in the YouTube. And then you must have a very good speaker, because the lousy speaker cannot differentiate 15 kilohertz and 20 kilohertz. You must have a good speaker, then you see at which point you will not be able to hear anymore. Okay, that is where your limit is. So as you grow older, our range becomes smaller and smaller. Clear so far? So 20 hertz means, what does hertz means? Hertz is the unit for frequency. And what does hertz means? Hertz actually means the number of times it oscillate or vibrate in 1 second. Okay, so we can hear sound that is produced by 20 vibration in 1 second, all the way to 20,000 vibration in 1 second. Okay, that's the hearing range of human. Okay, so different animal have different hearing range. Okay, so from 20 hertz, okay, the smaller number, you will hear a very low sound. Okay, like this, very low. Okay, very low sound. Then for 20 kilohertz, it's very high pitch. Okay, very high pitch. But most of the time, the sound that we hear doesn't stretch all the way to 20 to 20 kilohertz. Maybe it's more like from 20 to 2000 hertz. Because 2000 hertz is really very sharp. Okay, so far? Okay, so first of all, to have sound, you must have vibrating sources. Okay, you also need to have a median. Okay, you need to have a median. No median, if it's vacuum, you will not hear anything. So how many space movie do you all watch? You all hear a lot of like crackling sound, burning sound, explosion sound. By right, you cannot hear all this in space, because space has no matter, right? It's a vacuum. So if it's a vacuum, there's no medium to transmit sound wave, you will not hear anything. So in a lot of movies, when you hear explosion, boom, okay, in space, or you can hear the sun or the star, okay, burning sound. All these should be silent. Okay, space should be silent. You shouldn't be hearing anything in space. Okay, because space has no medium, you will not be able to transmit any sound wave. You will not be able to hear anything in space. So for example, okay, Hao Ming and Wen Xuan, both of you are astronauts. Okay, if you are from China, you'll be taikonaut. If you are from Russia, you'll be called cosmonaut. Okay, if you are American, you'll be called astronaut. Okay, so if both of you are in space, okay, if you want to talk, how do you talk to each other? How Ming say what's that? Wi-Fi. Okay, so to talk to each other, you all need to have contact with each other. So both of you will be wearing helmet, am I right? If there's a vacuum between you will not hear each other. So you must put your helmet together, touching each other. Then you can hear each other. Is that clear? That is if your environment is vacuum. Of course, in a spaceship, when there's air right inside, you can talk to each other. Okay, but in the open in the space, okay, when you're doing a spacewalk, okay, where it's vacuum all around you, okay, your talk, you will not hear each other, okay, unless you all hold a string and then hold on to a string, okay, that is connected to both of you, and then you all talk to the string, okay, then you can hear each other. If not, for you all to hear each other, you need to have a certain contact. Okay, maybe helmet touching helmet, then there is certain contact, then sound wave can move from one end to the other. Is that clear? Can? Okay, so I've talked about A. Let me talk about B now. Okay, so earlier on, I mentioned that all sound waves are longitudinal. Okay, all sound waves are longitudinal, meaning that the vibrating source, oh sorry, not vibrating, the vibrating medium are all vibrating parallel to the direction of the sound wave. I repeat myself again. If the sound energy is moving from left to right, okay, the particles or the medium will be vibrating parallel to the direction of the sound energy, meaning that you vibrate left and right. Clear? And when they vibrate left and right, certain part of the wave, when they are close together, it's called compression. Later I'll show you some charts. Okay, if they are far apart, if they are spaced out, the term is called rarefaction. Okay, so you all must know, okay, they actually vibrate in the parallel to the direction of the energy. Okay, when they vibrate close together, it's called compression. If they vibrate far apart, if they space out, it's called rarefaction. Clear? So later I'll show you some example. Then we'll need to identify what is the amplitude lah, what is the period lah, what is the wavelength and so on. Okay, of a longitudinal wave. Understand? Okay, so we just move on first for B. Okay, so for part C, we also need to know, okay, that sound wave, for it to move, you need a medium. Okay, I mentioned this many times. Number two, do you all know that the speed of sound is different in air, liquid, and solid? So can you make a guess? Sound travel faster in air, liquid, or solid? Okay, Wenxuan, well done. How many? Okay, do you all know why? Why does sound travel faster in solid? Okay, very good. Because in solids, the particles are closer together. Okay, so actually you can transmit the sound energy faster because they are all very close to each other. How about for electromagnetic spectrum? Okay, for EM wave, like light wave. Do they travel faster in air, liquid, or solid? Okay, for light, does it travel faster in air, liquid, or solid? Okay, very good. So for light itself, for EM spectrum, whether is it X-ray or radio wave or light, okay, they travel the fastest in vacuum and the slowest in liquid or solid, provided that the medium allows the EM wave to pass through. Okay, light cannot pass through all solid, am I right? Okay, so if you can pass through the solid, you actually slow down. Okay, light actually moves slower. Okay, in a glass, okay, in water and so on. Okay, so it's opposite of sound. So are you clear about this? Okay, so for sound wave, okay, it actually moves fastest in a solid, followed by liquid, followed by air. And then in vacuum, it doesn't even move at all. Okay, there's no medium. Understand so far? Okay, I will skip part E because it's easier to explain using graph. Okay, but you need to know amplitude of a sound wave determine the loudness. Okay, just remember first, amplitude of a wave, of a sound wave, determine the loudness. Meaning, the greater the amplitude, the louder the sound. And then the greater the frequency, like this, 20 kilohertz, very big number, right? The higher the pitch. Okay? The lower the frequency, like 20 hertz, the lower the pitch. Okay, so you need to know how to see this in a graph. And I'm going to show you some example now. Okay, today. Okay, so for next one, part F, you also need to know that sound can also reflect just like light. And then when sound reflect, you will hear the sound, a reflection of the sound. So the reflection of the sound is called echo. So that's echo. Basically, you can hear a lot of the repeating words because sounds hit maybe the wall, bounce back. So you hear the sound being dragged on. If the wall is far away, you will hear the sound, okay, at different interval. But if the wall is actually very near, your sound can be dragged further. So I'm in the room, I close all my window and door. Do you realize that my sound is a bit draggy? Meaning that it's not crisp, not sharp. You realize that? Okay, that's because there's a lot of echo in the room. Okay, there's a lot of echo in the room. If I were to open my door and my window, you'll realize that the echo will be gone. Okay, let's test the difference. Let me open my door. Hello, I'm back. Okay, so now my door and my window is both open. Can you hear that my voice is now very different? So earlier on, there may be a bit of echo. Now there should be very little echo. Can you hear the difference? No difference. Okay, for me in the room, I can hear a big difference. Okay, because earlier on, when I close the door, I close the window, there is a lot of bouncing, a lot of reflection, a lot of echo in the room. Okay, but if I were to open the window, open the door, the sound actually able to escape. So you hear less echo. So Hao Ming cannot hear the difference. How about for Wenxuan? Can you hear the difference? Now it should be a bit sharper, my voice. Also no. Okay, I go and close back the door. Wait. Anyway, you all have your own bedroom, right? If you all close the door and then sing, versus you open the door and sing, do you all hear the difference? Or in your bathroom, you close everything and then you sing. Okay, you should be able to hear some difference, right? The difference because there's a lot of echo. Okay, so the refraction of sound will produce echo. And echo can be used to measure distance. Okay, because we all know how fast a sound moves in the air. Okay, how fast a sound moves in water and so on. Is that clear? So since we know the speed of sound, and then we can use echo to actually quite reliably measure far distances. Is that clear? Okay, so Hao Ming has just mentioned to me what is the speed of sound in air. Wenxuan, do you all remember what is the speed of sound in air? Okay, so all of you remember that the speed of sound in air is about 330 meters per second. Okay, so this figure can be as slow as 300 meters per second. It also can be as fast as 340 or 350. So it depends on the air density. Okay, but 330 is quite a good gauge of how fast a sound moves. Do you all remember how fast a light moves in air? Okay, sound actually move at 330 meters per second. How about for light? You all remember how fast light actually move in air? How many you forgot? Wenshan, do you remember how fast light actually move in air? Okay, Wenshan, that is very good, but you need to put in the unit. Okay, I must emphasize myself again. Unit is very important. Please put in the unit. Okay, so light actually travel much faster. 3 times 10 to the power 8 meter per second. So when you're young, as your parents or your school teacher ask you, why do we see lightning before hearing thunder? Okay, do you all remember this question? Okay, this is the answer. Okay, you all learned this in Sec 3. Okay, light travel faster than sound. Okay, therefore we see lightning before we hear thunder. Is that clear? So if you hear a thunder about 3 seconds after you see a lightning, roughly how far is the lightning? Okay, if you hear the thunder only 3 seconds after you see the lightning, so how far do you think is the lightning from you? Huh? Okay, that's because light travel at 3 times 10 to the power 8 is almost instantaneous. This speed is like what? Traveling around Earth like 7 times in 1 second. Okay, something like 7 times in 1 second or 10 times. Okay, or something like that. Okay, so you can treat this as like almost infinity. Okay, whereas a sound only travel 330 per meter per second, right? So 3 seconds for the sound to reach you, it will take about 1 kilometer of distance. Okay, so you need to know the formula. Speed is equal to distance over time. Okay, if the speed is 330, the time is 3 seconds. Okay, the lightning is about 1,000 meters away from you. Is that clear? Okay, you don't divide by 3, Wenshan. You understand what I'm trying to say here? Okay, if the speed of the sound is 330, and if it hear 3 seconds later, your distance will be about 1,000 meters away. Okay, that's assuming your light, because you can see, light travel 3 times 10 to the power 8 meter per second. So, 3 seconds, in 3 seconds, light is actually traveling much greater than 1,000 meter. Am I right? So we can ignore how far the light travel in 3 seconds. Okay, we can ignore how far the light travels in 3 seconds. Okay, so if you hear a thunder about 3 seconds after the lightning that you see, okay, you know that the lightning is about 1 kilometer away. Okay, likewise, if you are far away, you see fireworks. Okay, during events like National Day Parade. Okay, sometimes you can see the fireworks far away. Wow, got light. But only after like 10 seconds later, then you hear the sound. Boom, 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 boom. Then from this, you can also roughly estimate how far the fireworks are. Is that clear? Okay, so have you all thought of this before, or is it the first time you hear about this? Okay. Okay, so by knowing the formula of speed, okay, by knowing this formula, speed is equal to distance over time, we are able to actually measure distance, okay, because of this thing called echo. Okay, what I explained just now about lightning, that one is nothing to do with echo, but you also use the same idea of speed is equal to distance over time. Okay, but for echo, it's a bit different. Okay, for lightning, you may be here. The lightning is here. Okay. So this is the distance the sound actually moves. Okay, so that you use the formula, you know the distance, you know the timing. Okay, sorry, you know the speed, you know the timing, you should be able to determine the distance. Okay, that is for lightning fireworks. Okay, how about for echo? How does echo work? Okay, echo is a similar but slightly different. How different is it? Let me show you. You are here, you have a wall. Okay, a wall or a ground or whatever. Something you want to measure the distance. Okay, so it may emit a sound wave. The sound can be a sound, it can also be ultrasound. Okay, the sound will actually travel all the way to the barrier or the wall. It reflect and come back. Okay, so this is the distance traveled by the sound. Okay, so you know the speed of the sound in the air or liquid, and you know you go and calculate the time taken for you to get back the sound. You can measure the total distance to and back of the sound. Is that clear? Okay, because the sound go there and then there's an echo, it come back. So that is the 2 times the distance. That's how far the sound actually moves. Okay, so for echo, it's a bit different. The distance that you measure is going there and back. Okay, things like this, where there's no echo, things like this, like starting a race, okay, or you see a lightning, see firework, it's just a direct distance. Okay, you hear the sound, you start to measure, you see the lightning, you actually measure the time in which you hear it. That's the direct distance. Okay, but for echo, the distance travel is double the distance. Is that clear? Okay, so this is something that you need to take note. Because once you understand, there's no need to memorize 2 or 3 formula. Basically, they are all the same formula, but one got ×2, one don't have ×2. You get what I mean? Okay, once you understand, you just need to apply the formula properly. Okay, so earlier on I mentioned this is the range, the frequency of range of sound that our ears or human can hear. Any frequency that is above this, okay, maybe like 50 kilohertz, okay, we cannot hear. So any frequency that is beyond 20 kilohertz, there is this special word we call ultrasound. Okay, so any frequency that is very high, that is beyond our hearing range, we classify that it's still a sound. Okay, we classify the sound as ultrasound. Is that clear? Okay, and what is ultrasound used for? Okay, for now, you all need to know. You can use it for quality control or for baby, okay, in the tummy, for pregnancy. Okay, so for now, I've gone through all the learning outcome that you all need to know for this topic. Any question for me? Okay, so far, is it useful? Or you already know everything that I mentioned? Because this topic is actually not hard. Okay, so let's go into the notes. Okay, so as you can see, for your there are 22 topics. Next year there's only 20 topics, so there's no more sound next year. But everything that is in that you learn in sound will be all squeezed into wave. Okay, so your juniors are not learning lesser. It's just that they actually change into lesser. They just actually reorganize the topics, and they got one new topic called radioactivity. Okay, so that is what's happening. And then for the earlier topic like here, kinematics to pressure, they also reorganize and put lesser topic, but they still learn the same thing, even though they got less topics. Actually, I don't know why they do that. Okay, so let's continue about sound. Okay, the definition of sound is a form of energy transferred from one point to another. Okay, that's the definition of energy, right? Okay, is a form of energy transferred from one point to another as a longitudinal wave. Okay, so can you see here? For a loudspeaker to produce sound, your source of the sound has to be a vibrating source. So when you touch the speaker, you can feel that it's vibrating. Okay, so the vibrating sound, okay, so the vibrating speaker, in this case, the vibrating diaphragm in the speaker will actually make the air particle move. So when there's no sound, the air particles are all equally spaced out. So individual particles, they will actually move. Okay, so you look at the bottom drawing here. Okay, look at the, hold on for a while. Hold on now. Okay, so can you see at the bottom here? When there is no sound, let's assume that all the air particles are equally spaced out. So they are not moving, they are all equally spaced out. Okay, they are just minding their own business. Okay, but when there is sound, they'll be all vibrating. How? Okay, as a longitudinal wave, the particles will be vibrating. Okay, the particles or the particles in the median. Okay, let me type out. Okay, so the particles in the median will vibrate parallel to the direction of the energy. Okay, so if the sound energy is moving from left to right, the particles will be vibrating parallel. Basically means you vibrate left and right, parallel to the direction, okay, to the direction of the energy. Clear so far? So when they are all close together, we call compression. Okay, when they are far apart, we call them rarefaction. Okay, so in this graph, okay, this graph is air pressure versus the distance along the pipe. So can you see here? They are all very close. The pressure is very high. Here, they are all spaced out. Okay, here they are all spaced out. So the pressure is very low. Okay, so this zero line here is the equilibrium distance, the pressure. When there's no sound, this will be the pressure of the air at the point of time. But when the particles are close together, we call this compression. The air pressure is higher. And then here, where the air particles are spaced out, the air pressure is low. Okay, so this part is called rarefaction. So compression, close together. Here, spaced out, rarefaction. They close together, compression, spaced out, rarefaction. They close together, high pressure, spaced out, low pressure. Clear so far? If you understand, give me a yes reaction. If you don't understand, give me a no reaction. Hello, are you there? Are you there? Hao Ming and Wenxuan, are you there? Okay, you all get it already, huh? Okay, so what is one wavelength? Okay, wavelength will be the continuous same point. So the tip of the high pressure and the tip of the next high pressure, the length between two consecutive compression is one wavelength. Okay, he also can use the lowest air pressure point. So at the consecutive rarefaction point, like here, from here to here, From one rarefaction to the next rarefaction, you can also say this is one wavelength. How about we use 0? Can we say this 2 consecutive 0? Can I say this is one wavelength? Can I say this is one wavelength? Because it's consecutive 0, ma. Can I say this one wavelength? Okay, so yes, they are both 0, but this 0 is going up. This 0 is going down. This 0 is going up. So I cannot use the going up 0 and the going down 0 as the consecutive, the same point. It must be the same going up 0. Okay, so for you have to use a 0 point, can? It must be from this point to this point. The 2 consecutive 0 where it's going up. Is that clear? Okay, that is one wavelength. Okay, you cannot use the 2 consecutive 0, but you can use the 2 consecutive 0 that where the wave is going up. Clear? Okay, let's continue. Okay, so can you see here? I mentioned earlier on, the particles in the medium will vibrate parallel to the direction. So can you see this first particle, it actually move here. Okay, so it actually, the energy is moving from left to right. Okay, so the particle will only move left and right, not up and down, but left and right. So they're moving in the parallel to the direction of the energy. It's called longitudinal wave. Are you clear about this? If the particles is vibrating parallel to the direction of the energy, okay, we call this longitudinal. Clear? Okay, so when there's no wave, this particle is at this equilibrium point or the resting point. Okay, so this is the displacement of the wave. Okay, so this arrow here, there's a word we call displacement. Understand? So can you see this arrow is long, then become not so long, then become short, then no arrow, then short, not so long, and then very long. So we call this the displacement. This particle is being displaced from the equilibrium. Understand so far? Okay, so if you have learned amplitude in the topic of wave, what's the definition of amplitude? Amplitude means the maximum displacement of the particle. So can you see? The particle move this distance. This is the displacement of the particle. This is the displacement of the second particle. This is the small displacement of the third particle. Particle P does not displace at all. Can you see that? Then the next particle moves slightly to the left. The next particle displaces more to the left. Then the next particle here displaces a lot to the left. So this is called displacement. So what is the amplitude of the wave? The amplitude of the wave will be the maximum displacement of the particle. So you look at all these displacement. Okay, let me just highlight. The displacement are this. This is the displacement. The longer the displacement. Okay, so which one has the longest displacement? So all the thing I'm highlighting is the displacement of the particle. Understand? Okay, so the longest displacement, the maximum displacement like this one here, is the amplitude of the wave. Understand so far? Okay, it's the same idea for transverse wave. Transverse wave, the particle will be moving up and down, correct? Will be vibrating up and down. So some of them will vibrate very high. Some will be not moving. Some will be a little bit below. So the maximum displacement is the amplitude. Are you clear about this understanding? Okay, because a lot of students, when we say that amplitude is the maximum displacement, when we say maximum displacement, you have to understand what it means. So for today, I mentioned maximum displacement. Do you understand exactly what I mean now? Okay, yes or no? Give me some reaction, please. Okay, good. Okay, so you appreciate the understanding of maximum displacement. Then there's no need to memorize the definition because you understand already. Okay, that's what my aim for you to understand so that you all need to remember less. Can? Okay, so can you see over here? And this one, the displacement is the longest. Okay, can you see here? The displacement is the longest, so therefore it has a high displacement. Okay, this one, the displacement is in the opposite direction, so you have a negative high, you have a very negative amplitude. Is that clear so far? So let me repeat myself again. Amplitude, can you see the word A here? Amplitude of a wave is the maximum displacement, okay, of the wave. Is that clear? Amplitude of the wave is the maximum displacement of the wave. Okay, so this is the part where it is the maximum displacement. So this is the amplitude. Okay, so this is your amplitude. Okay, which is your this distance here. Okay, so this length here is your amplitude of the wave because it's the maximum displacement. Okay, the highest point, the furthest away from the equilibrium. Zero is your equilibrium. You actually move the furthest away from the equilibrium. This is your maximum displacement. So your amplitude is your maximum displacement. Okay, the maximum displacement is from zero. It's not A to minus A. Okay, it is the maximum displacement. The maximum it goes displaced from zero. That is your maximum displacement. That is your amplitude. Okay, it's not from A to minus A. This distance is not amplitude. Okay, amplitude is from zero to the maximum displacement. So that is your amplitude. Is that clear? Can? Okay, so this is a displacement distance graph. If it's distant, okay, if it's distant, you know that from here to here, this is one wavelength. Or you can use maximum point to maximum point. So these two are the wavelength. Is that clear? If we use the distance as the x-axis, okay, the one wave is called a wavelength. However, in this case, if we use time as your x-axis, okay, this one wave is called one period. Okay, the period. Are you clear about how to see the two type of wave? The two wave looks exactly the same. One is measured against distance. So for measuring against distance, you can determine the, sorry, I write the wrong word. I write the wrong word, sorry. Let me erase. Okay, you can find the wavelength. So one wave is one wavelength. Is that clear? But if you draw a graph against time, one wave is one period. Understand so far? Okay, so this is your amplitude. Okay, so wave can be plotted against distance or time. If it's distance, one wave is wavelength. If it's time, one wave is one period. Are you all confused? Or are you all okay? Okay, if you're okay, give me a yes reaction. If you're confused, give me a no reaction. Okay, very good. So I hope this is also a good revision to your wave topic. And maybe that's why they combine the sound topic with the wave topic. Okay, let's continue. Okay, just let me read out to you all. Compression is where the air pressure is higher than the normal pressure. So that's when the particles are close together. Okay, rarefaction is where the air pressure is lower than the surrounding air pressure. That's when the particles are spaced out. Okay? And sound is produced by vibrating source. Okay, and it is moving. Sound actually move in the form of longitudinal wave where the air particles vibrate parallel to the direction of the wave motion. Okay, so do you understand this part? Okay, so these 4 points, if you all are clear, give me a yes reaction. Okay, thank you, Wenxin. Thank you, Haoming. Okay, transmission of sound. Okay, this one I mentioned just now already, so let me go through very quickly. Sound require a medium to propagate. So when there's no medium, meaning in vacuum, you cannot hear sound. Okay, you also know that sound travel in fastest in solid. Okay, so in solid, maybe traveling around 5,000 meters per second. So when you talk to a string, you will be faster than you talk to air. Okay, so when you're swimming, when you hear sound, the sound is actually traveling about 5 times faster compared to air. Okay, so for speed of sound, it travels the fastest in solid, okay, followed by liquid, followed by air. Okay, the reason is because in air, in solid and liquid, the particles are closely packed together, so they can actually move faster. Okay? Okay, so how do we measure the speed of air, the speed of sound in air? Okay, how do we measure? Okay, it's just like you're in a racetrack, in a 100-meter racetrack. You have a determined distance, maybe 500 meters. Okay, it cannot be too close. Okay, it cannot be too close. Okay, then you have a gun that will produce smoke. So you as an observer, when you see smoke, you on your stopwatch. When you hear the sound of the gun, you stop the stopwatch. Okay, so and then you use the formula distance over time. You know the distance, you calculate the time, can you find the speed of sound? Is that clear? Okay, so how do you improve the calculation? So you do the experiment a few times and take the average. Okay, number 2, you can also switch position because wind actually also influence the speed of sound. Okay, because the wind carry the particles, right? So when they carry the particles, it's also like carrying the sound. Am I right to say that? Okay, so you switch position. Okay, you can also try to eliminate the presence of wind. Okay, that's assuming that the wind is constant. Understand so far? Okay, so are you clear about measuring the speed of sound in air? Okay, if you are clear, give me a yes reaction, please. Okay, thank you. Let me continue. Okay, so we are ending already, but before actually there is no never mind. Okay, reflection of sound is called echo. So I already mentioned when a sound moves to a wall and then it reflects back, what you hear is called the echo. Okay, so echo can be used to also measure large distances. Okay, and because it can measure distances, it can also try to detect object. So it's very useful in like radar. Okay, so some things like radar is something like using echo to actually detect object, also to measure long distance. So how do we do that? So for example, we have a sea and we have a ship. Okay, so you want to find out how deep is the sea. So your ship will emit a sound. This sound can be normal sound. It also can be ultrasound. Okay, so the sound, so you have this thing called the emitter. It will emit sound wave. When it hits the bottom of the sea, okay, it will reflect. This reflection is called echo. So the sound is actually traveling back. So in your ship, there's another thing called the receptor or the receiver. You receive or or is the detector. Okay, the receptor or the detector will detect the echo of the sound. So there is this time 1 and time 2. So you know the distance, the difference of the time. You know how fast the sound travel in the water, about 1500 meters per second. Okay, you know the time, you know the speed of sound in water. Can you measure how deep the sea is? Can you do that? Okay, same thing. Use speed equal distance over time. But remember, this distance that you calculated is the 2 times the depth of the sea. So whatever distance you calculated, you have to divide by 2. Is that clear? Okay, if you are clear, give me a yes reaction. Okay, let me talk about part 5 first. Part 5 actually more important than part 4. Okay, so sound can be plotted in amplitude, amplitude versus distance graph. Am I right to say that? Okay, or you can also use time. Either one is the same. So a normal sound wave can be like this. Is that clear? Okay, so amplitude is how high, how far it displays from the zero. So the maximum displacement is the amplitude. Okay, so the greater the displacement, okay, the greater the amplitude, the louder the sound will be. Is that clear? Okay, so the larger the amplitude, let me use the black color. Okay, why my black color disappear? Okay, I use the blue color. Okay, wait. Okay, the larger the amplitude, my amplitude is bigger. Can you see this? The louder the sound will be. Okay, so the blue wave will be louder than the red wave. Is that clear? Okay, I repeat myself. The blue wave will be louder than the red wave. Okay, because it has a greater amplitude, the greater maximum displacement. Understand so far? Okay, then we talk about frequency. The higher the frequency, the higher the pitch. Okay, what does a high frequency means? Means every second it has more wave. So can you see? The green wave will have a higher pitch compared to the red wave. I repeat myself again. The green wave will have a higher pitch compared to the red wave. Yeah. Okay, so from a graph, whether is it amplitude distance graph or amplitude time graph, they will show the same pattern. The greater the amplitude, the louder the sound. Okay, the more wave you see in 1 second, okay, you will also get the higher pitch. Is that clear? Okay, so Hao Ming and Wenshen, if you understand this, give me a yes reaction. Okay, very good. Okay, now the last part of this topic will be ultrasound. So earlier on I mentioned human range on audibility as a baby, a pure perfect human is from 20 hertz to 20,000 hertz. Okay, the higher this number, okay, means the higher the frequency, means the higher the pitch. So as we grow older, we will not hear 20,000 hertz. Maybe for me at my age of 40, I can hear up to maybe 15,000 hertz. Then for you as a 15-year-old child, maybe you can hear until 18,000 hertz. Okay, for baby, maybe 20,000 hertz. Is that clear? So how high can you hear? You may want to actually go to YouTube, go and find the sound frequency videos, and also a good speaker. You see at which range can you hear the sound. Understand so far? Okay, so what is ultrasound? It's also sound, but sound that we cannot hear. Okay, ultra means okay, where the frequency is greater than 20,000. Okay, so the ultrasound is actually at a higher frequency. Okay, since it's beyond the 20,000, we will not be able to hear it, but it is still called sound. Okay, that doesn't make sense, right? It's a sound that we cannot hear, so we call it ultrasound. Okay, so ultrasound actually can be used for a lot of things. Okay, first of all, it can be used for quality control. Okay, like check for crack lah, and so on. Okay, the idea about using ultrasound is the same as echo to find distance as well as to detect object. Okay, so for example, this is a mommy with a baby inside the tummy. So the baby, the head is below, right? Okay, so the baby. Okay, so you will have ultrasound. Okay, ultrasound. You will have both the emitter and the receiver in the ultrasound machine. It will detect when you reach certain surface, it will actually come back. Okay, then you'll use this technology by counting how long it takes to receive back the ultrasound, and then you can form a picture of what's inside. Okay, and why does this work? Because ultrasound can actually go through solid, okay, compared to eye. And therefore, using this technology, you can actually try to get an image of what's inside your tummy. Okay, then what about X-ray? X-ray, let's say this is the person. The hand is here, and the head is here. X-ray is a bit different. X-ray, you will have the emitter here that produce X-ray, and then you will have the film behind. So the X-ray will try to go through the person. It doesn't go through the person, the film will be white. It will not get exposed. Okay, the part where X-ray that actually hit the film, the part that hit the film will get exposed, and you'll become the black color part. Is that clear? Have you all seen before images of X-ray? Okay, so maybe I show you all some image of X-ray. Hold on. Okay, let's look at this one. Okay, so you look at this skull here. Okay, on the surrounding part like here, there's nothing blocking the X-ray, right? So the film actually get very exposed, become black color. Is that clear? However, your bone block part of the X-ray. So the film is no longer exposed, therefore it become white. Is that clear? So now you understand how X-ray work? Where the X-ray able to penetrate, you'll get black color part. Part that it actually doesn't get exposed means that it's being blocked. So it actually block the X-ray from going through. So your film will become white color. Okay, that is how the X-ray works. Is that clear? Okay, if you understand this part about X-ray, give me a yes reaction, please. Okay, let's try ultrasound. Okay, so can you see this picture here? This is like a image of an ultrasound baby. Okay, ultrasound baby. So basically, there's actually it's actually more complicated compared to X-ray. Because how the image is formed, they need to calculate how much time they actually receive back the sound. Then from there, they were actually able to create the image here. So this image is not because the sound can actually produce image. You need to calculate how much, okay, like at each point of the picture, how long it takes for the sound to return. So for example, like here, this part, okay, you don't see anything, means the sound never return. Is that clear? Okay, so for ultrasound, it's not using sound. It's not because sound can see things. Like X-ray, okay, X-ray, when something block it, you form an image. But for ultrasound, there's a lot of calculation involved, okay, based on the time it takes for the sound to come back. Then from there, you're able to form an image like this. Is that clear? Okay, that is how an ultrasound machine works. Understand so far? Okay, so before we end, let's listen to sound pitch frequency. Okay, let's see whether can we hear certain sound. Hold on, hold on. Okay, let's try this one. You're on your speaker loud. You see how high can you hear a sound? Can you hear something? You see, even though the frequency is about 200 hertz, the pitch is really quite high. Did you realize that? Okay, imagine at 1000 hertz. By the way, if you hear something, can you give me a thumbs up? Okay, it's very high pitch already. I can still hear it. Can you still hear? Okay, I think I cannot hear already. Can you hear? Okay, so you go and Google how high frequency can you hear? Then you go and see how bad your hearing is now. Okay, so for me, about 15,000, 14,000, I really start to not able to hear. So for you, you're going to try, get a good speaker, go and listen. See how high frequency can you hear. Because the older you are, the higher the frequency, the lower you can hear. Okay, the lower maximum frequency you can hear. So can you imagine ultrasound? There are still sound moving in the air, just that our ear cannot capture. Okay, and then it's used for things like scanning the baby and so on. Okay, so that is all for today. How do you find today's lesson? Okay, so today, can you please do a few things? Okay, let me write down. Okay, homework. Redo the EM spectrum Kahoot. Okay, make sure that you do 100%. Okay, if you got time, we watch this lesson. Okay, so the checkout question I have for you. One thing I learned today. Two, how much you learn today? 1 to 10. Okay, how well Mr. Chu teach today? 1 to 10. And lastly, how can the lesson be improved further? Okay, give me your answer to this. Once I call your name, you may leave the class. Okay, Wenxuan says maximum displacement equal to magnitude. Well done. We will do the O-level question next week lah. This week is a theory. Okay, next week, next 2-3 weeks, we'll be doing the practical, the practice. Okay, thank you, Wenxuan. I will see you again next week. Good night. Okay, Hao Ming, how about you? Okay, how do you want me to do experiment, Hao Ming? I did the experiment on how high you can hear the sound frequency. Okay, thank you, Hao Ming. I'll see you again next week. Okay, good night. Goodbye.